I was planning on it today, but we got like 15 minutes left. So. I'll get you a work day tomorrow. At least most of the day, if not all the day tomorrow. Tuesday I've got carved out, and next Thursday our work day. Monday we're gonna do stuff. It's a short day, so we might as well do some stuff in here. Okay, here we go. Yes, ma'am.
So are we done with optimization?
I'm done teaching it. You don't have to be done doing it, but I'm done teaching it. Yeah. Yes.
Do you have to retake graded?
No, I don't. I'm not going to grade them until. I'll tell you what. So we'll go. Tomorrow will be a day where people could do those, and Tuesday will be a day. But after Tuesday, they're done, and then I'll grade them. Okay. And I want to grade them all at once. Okay, so let's take a look at this. We're talking about stuff we started yesterday, right? We started with calculus Jeopardy. We called that. Say it again.
And we ended with physics.
We ended with physics, yeah. So we ended up learning a process called antidifferentiation. Okay, that's I want to just today is going to be a day. So today's a day about just taking what we did yesterday and turning it into something more mathematical. We're going to learn the notation, learn what it looks like in calculus, but the concepts are the same. So we did stuff like this, right? We started with a differential equation. And what did we say the definition of a differential equation was?
Calculus Jeopardy.
Yeah, it's an equation with one or more derivatives. Yeah, that's it, right? So our goal with the differential equation is to undo the derivatives and play calculus Jeopardy. Find the function that we would have differentiated to get that derivative, right? So we've got something like this, right? Okay, well, we skipped a section, which I don't feel bad about. There's a section at the end of chapter 3, I think section 3.9, has to do with differential approximations. Not a big deal. Really not a big deal. That's something you'll cover like one day in college, and it fills in a small blank. Not a big piece of the big picture, though. So one of the things they talked about in 3.9 was the idea of rewriting all the derivatives that we have in a different form, called the differential form. And what that would look like is just this. So if we had, for example, the derivative with respect to x of sine x, what's the answer? Cosine x, right? Okay, so that's what we might call quotient form of the derivative, where we write it as the derivative of something with respect to x. Okay, what we can do to put this into differential form is to just take the same derivative, and there's two ways to think about this. I think the easiest way is to think about algebraically multiplying each side by whatever is on the bottom of the derivative, so dx in this case, right?
Yeah.
So what would we get then? Well, we'd get the derivative of sine x equals cosine x dx. Same thing, only that's in what we call differential form. Let's put all the phones away, please. Okay, so what's the point of that? Well, they serve sort of different purposes, which we're going to see here over the next week or so. When we talk about a quotient form like this is useful when we're thinking about things in terms of slopes. So like when we talk about dy dx, for example, we know that that's the rate of change of y with respect to x, which graphically is the slope of the curve, right? Okay, that's fine. That's very useful to us. This is a little bit different. This is like saying, okay, if we break the change in this function up into really small pieces, what would those pieces look like? They would behave like cosine x times whatever the thickness of the slice was, dx. Okay? We could really just use the chain rule and get from here to here using what we already know. Okay, so if we want to take the derivative of hand with respect to x, well, what's the derivative of sine of something? Cosine of something, right? So the derivative of sine hand is equal to cosine hand, right? Well, what's hand?
X.
It's an x. Now, if we just take the derivative of x, we're not taking it with respect to anything. What do you think the derivative of x is? Well, it's dx, right? Because we're not, now this is different. We're not saying, like, if I take the derivative with respect to x of x, the answer is 1, right? But that was different than taking the derivative of y with respect to x, right? The derivative of y with respect to x was y prime, or dy dx, right? Remember this stuff? Okay, well, what if we don't specifically differentiate with respect to any variable, right? The reason this was 1 is because it was really dx over dx, right? Which just turns into 1. What if we're omitting that bottom part of the derivative? If we're not differentiating with respect to anything, we're just differentiating. Well, then the derivative of x is a variable, and so the derivative of x would just be dx, okay? So there's really two ways you can ultimately look at this differential form of a derivative. You can just think of it sort of algebraically as being a regular derivative, a ratio form, just multiplying both sides by the denominator to get rid of it on one side. That's fine. Alternately, you can look at it as differentiating without respect to anything and just following the chain rule. Okay? So why did we do all this stuff? What's the value of all this? Okay, here's the value. Because when we solve differential equations, yeah.
I'm really sure that blue came from that one you just erased.
Say it again. Can I restore it? Yes.
Probably.
Yeah.
Yeah, the blue thing, where, it's like a random equals cos.
Well, okay. Oh, where'd it come from?
Yeah.
It's just from here. So all we're doing is we're just saying this equals this, or this equals that.
Okay, so
Same
it just
thing.
should be like that.
Yeah.
That's what you just wrote.
That's a little different.
Okay. Well, the ways, there is no difference. The difference was just the ways we got it. One was method 1 was just to say algebraically, just take this and multiply each side by dx so those cancel. Method 2 was to say, okay, let's start with this and let's just differentiate using the chain rule. We'll use differentiate using differential form. Okay. But the outcome is the same in either way. Okay, so now, why do we do this? All right, here's why we do this. Here is how we technically solve a differential equation properly. We don't actually just play calculus Jeopardy. We write it in a little different form. We do this. We take this differential equation, and we're going to multiply each side by dx to put it in differential form. Okay, so we end up with dy equals f of x dx. Okay, and now we got to come up with some notation. We come up with some notation here to tell us to anti-differentiate. Well, the notation is a little bit weird. The notation is this. When we want to anti-differentiate, we're going to take what's called an integral. Okay? An antiderivative is exactly equivalent to what we're going to call an indefinite integral. They mean exactly the same thing. Okay? So this is telling us this symbol, and what this is, that is a lowercase Greek sigma. So it's a lowercase Greek s, which stands for sum. And that's not going to make any sense to you right now, but we'll see in about a week why this actually works out to be a sum of some terms. And that's don't think about that at all right now. That's coming up later. But that's the symbol. So what does this do then? This tells us to play calculus Jeopardy. So what is the antiderivative of the derivative of y? It's y, isn't it? Right? It's y plus some constant, right? Okay, plus c. I'm going to call it c1. So this one gives us y plus c1. What is this one going to be? Well, I mean, we don't really know yet, right? It's going to be whatever it gives us. It's going to give us something that we could call maybe capital F of x, which is a different function, right, of x. For example, if this was a cosine, then this would be a sine, right? Okay. Plus some other constant. Okay. Say it again.
Wasn't it tiny?
Those were undoing.
Yeah, we're undoing it.
So you take
Right.
Wasn't it
Well, no, because, like, for example, let's put a value in there. What if it was something like this? What if this side were antiderivative of cosine x dx? Well, the derivative of what is cosine x dx?
Cosine x.
Sine x, right? Plus c, right? So it would equal sine x plus what we called C2. So this is just that.
The constant's not gonna be whatever D is.
No, the constant, because the constant, remember when we played calculus Jeopardy, when we differentiate, the constant goes away, because the derivative of a constant is what? Zero, right? So this went back to that whole idea yesterday. Remember that we took some derivatives. Let's do this real quick. Let's do one example, and then we'll jump back to this process. I want to make sure you guys can, it's really important that you attach what we're doing today to what we did yesterday. Yes?
So dx isn't like dx isn't like 2x.
No. It's not. Dx, really what this means is, you can almost ignore the dx. The dx is really, when we talk about a function like this part right here, in a different color, this part right here is, just the f of x is what we call the integrand. That is always going to be the function that you're playing calculus Jeopardy with, like we did yesterday. The dx is simply there because it's written in differential notation, right?
Okay.
So if we were to differentiate sine x, the derivative of sine x would be cosine x times the derivative of x, which is dx. See what I'm saying? Okay. You can kind of almost skip the dx part and just say, well, in regular derivative notation, what's the derivative of sine x? It better be the integrand cosine x. Okay. This will make more sense when we actually go through an example
So
or
you're
two.
saying with the cos, so the d of x is like no
The d of x you can literally think of as being part of the notation.
Like y
So-
prime.
So in fact, let me make the dx, let me make the dx pink. And so really, the only part that's unique to this integral, or this antiderivative, is the f of x. Every time we write one down, it's going to be the integral of something times dx. Or if it's dz, if z is our variable. Or dy, if y is our variable. Whatever our variable is, right?
Yeah.
Okay. Yes. So every time you do it, you're going to start off by writing the integral sign, some function that's going to change with each problem, and then at the end you'll always finish with dx. Or if the variable is something else, maybe it's theta, then it's d theta. But whatever your variable is, d that. Okay? They're like bookmarks, or like bookends, and this is the integrand. Okay? Integrand. Yep. Okay. So this is, then how could we write this solution then? So really what this becomes, why wouldn't we just combine both of these constants into one constant? Because they're just constants. And so our answer is y equals f of x plus some constant, call it c. Okay? So if we wanted to label this stuff then, we would say, let me just kind of start over. So we started with y equals the integral of f of x dx, which is equal to, our answer would be capital F of x plus c. Okay, so this is, like we said, that's the integrand. Integrand. This is the integral sign. This is the variable of integration. Okay? You can literally think of it as just reminding you what's the variable. It's a function of what variable? Well, dx in this case, right? So you can think of it as just being reminding you what the variable of integration is. And then this is the antiderivative. And this whole thing we would call the general solution. Okay? Okay, that's it. So,
Does the y have anything to do with it?
no, the y is just that our answer, we're trying to solve for what is y. Well, y is going to be this, right? Our answer is y. Okay? Let's do one. It's not hard. Let's do one.
Tracing it to.
You got like 2 minutes.
That's fine. We can do it in 2 minutes.
Yeah, 3 minutes.
Okay, so let's, what if we want to do, Okay, so let's solve this differential equation, right? Technically, I mean, we could play calculus Jeopardy and just write y equals what?
Tan X.
Tan x,
DX.
no, tan x
DX. Plus C.
plus c, right? Okay. I was waiting. The real intervening steps, this is how we would do the calculus, so to speak. The algebra would be to say, okay, well then dy, if I want to solve for, gosh, I'm trying to go too fast. If I want to solve for y, I would just say that y equals the integral of secant squared x dx. Okay? That's how I undo that. I'm going to multiply both sides by dx, and I'm going to anti-differentiate to undo the derivative, right? That's what they do. They're inverse in nature. They undo each other. So then that would just equal what? Well, what's the antiderivative of secant squared? Tan x, and then we got to add a constant.
Yes. And then you showed us that you're gonna find that constant. But you don't have to have the y plus the constant.
No, because this is my answer. So what we just found was, what was the function that we would have to differentiate to get that?
Tan x plus c.
Tan x plus c.
That's all. Can we find c from that?
Okay, if we could find c if I gave you an initial condition or a particular condition. So if I told you, for example, that x equals, or that y equals 0 when x equals 0, we could use that to solve for
Then you
c.
put it in